So, I don't know if you can hear me outside, but we're going to start again. And we had a couple of requests during the last talk. One of the requests was if we could keep the door closed during the talks, because it's a little bit cold by the door. And the other request that we had was, if you're in the audience, obviously here physically, if you could try to not talk while the speakers are talking. Some of the other audience members were saying that it was competing with the talk up here. So if you could just be, have your best D manners and just keep the chatter to a minimum, or maybe just keep the chatter to text. We are live streaming everything, so if you can't read any of the text up on the screen, feel free to jump on the live stream. It should be up on the DConf website. It's also on the DLangConf Twitter. So either way, you can get the URL there. And if anybody watching the live stream has any questions, just chat it over to Scott. He's on there. He'll throw it out to the mic. And if anybody here has any questions, just raise your hand and I'll run the mic over to you so that people watching the live stream can understand you better. That's it from me. I want to give the stage over to Simon. So take it away.
Is this on now? Awesome. Oh, I've actually got to start my slides myself, have I? Oh, I'm going to do that? Awesome. So g'day, I'm Simon Arneaud. As you probably guessed, I'm French name, but I'm not actually French, I'm Australian. But here I am going to talk to you about betterC. So this is some stuff I want to get through straight up front. So I'm going to bash C and C++ a little bit in this talk. But I want to say up front that yes, people are writing useful code in C and C++. They are useful, powerful languages. Actually, get some hands up. Who here is using C and or C++ professionally or in side projects or something? That looks like actually at least half the room. For me as well, actually I've used C and C++ professionally as well and in hobby projects for a long time before using D. So I think a lot of us here know that, yeah, these languages are actually useful languages. Next thing as well, got to be upfront about this. D is not something that water brought down from the heavens as like some perfect language that's going to save us all. It is actually a flawed language. If you're using D, I actually recommend having a look at this and familiarizing yourself with some of the problems that D does have. So I'm going to be upfront with that as well. But I think the real point here is that D is here today, and it's a better language for a lot of stuff. It's a lot more productive, and it's getting better faster and faster. So start off with a little bit of history. So Unix was originally written in assembly language. And around about 1970, Dennis Ritchie and Ken Thompson and a few others wanted to rewrite it for the PDP-11, and they decided to use a higher-level language, which was a little bit controversial for the time. And they looked at some of the languages they had, but they ended up deciding to write their own language. Now, I put there in the number 3 there, so there's sometimes a misconception that's spreading in the 21st century that C is like the first language that came after assembly. Just to make sure we're all clear, no, it's not. So this is the 70s we're talking about here. So like Lisp, COBOL, and Fortran all originally came out in the 50s. So C is not the first high-level language by a long shot. And you notice as well that it was originally designed as a kind of high-level assembly language for PDP-11. And if you understand that, you can actually understand a lot of the design of C. It makes a lot of sense. But C++. So Gus Strup was doing a lot of computationally intensive simulation stuff, and he was faced with a dilemma. So he could use languages like Simula that had high-level features that he really liked. And they were really convenient, but made things slow. On the other hand, he could use C, and his code would be fast, but then the development would be too slow and error-prone as well. So he thought, why don't I just add my favorite features from languages like Simula to C? So he did that. He created C with classes. And the way he did it originally, kind of interesting, he just made a preprocessor for C. So he would write his own C with classes code, feed it to this preprocessor, which translates stuff into C code, and would compile from there. So originally, by implementation, C++ was just a superset of C. But now they are actually separate languages, and they have actually diverged a little bit. They're mostly compatible, but they have diverged a bit. And here we get to D. So actually, we've got Walter Bright here, so maybe it's not really the best person to give the history here. Walter Bright, can you give anything about, yeah, that's you, yeah. Any couple of sentences about how you came to write the C++ compiler and how you came to write D?
Well, I came to write the first C++ compiler because I had a C compiler and I was looking for a way to distinguish it from the 30 other C compilers. So I saw this book called C++ in the bookstore, and it looked kind of cool. I thought it would take about a month to implement it. And fortunately, I was very naive, or I never would have attempted it. D came about because you can't work on compilers for a long period of time and not come up with, you want to do it differently. And that's what happened with D.
So I guess it's my job to elaborate on the why you want to do it differently. So yeah, why a new language? And why am I calling this, why is the title of this talk D as a better C and not D as a better C++? I mean, if C++ is meant to be an improved C, surely we should be looking for an improved C++. But reason for that, I think, comes down to this. So if you think about it, one of the things that makes C++ really powerful and really successful is that it was just an extension to C. But at the same time, especially nowadays, that's the main thing that's holding it back. So C++ doesn't really improve C so much as just build on top of it. And there's a lot of stuff that we could improve with C. So, I mean, what am I talking about here? What is actually wrong with C? So the problem with this question is actually no short answer. Now, luckily for me right now, I've actually got you all trapped in this room, so I can give you a slightly longer answer. But even that's not actually going to be the full answer. So I'll give it my best shot, and I hope I can convince you that there are some things to be fixed in C. We'll see how it goes. So first thing. So C is a compiled language, has types, it statically checks stuff, but it doesn't actually give you that much type safety. It gives you a lot to be useful, but it's hard to really lean on the type system to really get a lot of type safety. So in this example here, C supports creating new enum types, which is really handy. But you see at the bottom there, there's a bit of copy-paste mistake for accidentally assigning a reactor ID to a reactor mode. And C compiler doesn't complain about that at all. It's totally fine. This one here. So this one isn't really strictly a problem with C so much. It's just an example of how much you can screw with C without getting any sort of compiler error or complaint. So normally, if you have an array, you can index it with a number. It turns out that if you, for whatever reason, do it the other way around, you have a number and you index it with an array, that actually works fine as well, because indexing just gets lowered to excuse me, indexing just gets lowered to addition and dereferencing. So as I said, this is not so much a problem as just an example of how much you can mess with C and not get an issue. So C is very relaxed about this sort of stuff. D takes it something that if you're going to write code like this, something's probably gone wrong, and so D does not support this kind of screwing around. This one here, this is a really stupid mistake, and I'm going to guarantee I'm not the only one in the room who's made it multiple times, writing C code. So yeah, this is obviously meant to be an if statement. It's actually looking kind of small from here, but sorry about that. It's an if statement that's only going to launch the missile if we're ready. But of course, some of you have noticed there's a semicolon at the end of the first if statement. So that actually becomes a no-op if statement, and the braces are just an empty scope for the launch missile function. So this means we're actually launching the missile regardless. So D takes the position that there is actually no reason to have an empty statement with a semicolon. And so that's an error in D, you'll catch that. And that turns out to be a pretty practical way to stop a lot of these sort of bugs. So this is getting a little bit more technical, but constant and volatile are kind of not very good in C. So volatile, I won't go into it because thankfully not many people except embedded systems developers are using it that much nowadays, but it is a broken mess. Const, let's say here's not very useful as a compiled hint. We've actually got a talk, I think it's tomorrow, talking a bit more about how constant immutable effect compilers, so I won't go too much into it. But there's a popular myth that just never seems to die, that if you just throw lots of consts in your C and C++ code, then you'll help the compiler make it go faster. But you'll notice as you see in the talk later, that if you look at their output, it often doesn't make any difference whatsoever. And this is specifically C, not C++, because C++ did fix this. And C actually only handles one layer of interaction with const and volatile properly. And if you've ever used C extensively, you'll come across this problem. It's very annoying. So first off, you end up having to do a lot of typecasting that you shouldn't have to. And in fact, there are some implicit conversions that are unsound. So you can actually break constant correctness in C without using a typecast. And it's kind of ironic that C is considered a de facto standard for writing things like hardware drivers when standard C doesn't actually give you much that you need for that. So an example of what impact this has is consider the Linux kernel. It's been ported to a lot of CPU architectures, and a lot of board architectures as well, but only supports GCC compiler. It's a project to make it work with LLVM. It's a big project. I'm not sure how it's going, but the point is, it is a big project to do that. It's not something you get out of the box. But this is because you normally have to use compiler-specific pragmas to do a lot of the stuff you want to do when you're doing hardware drivers. Preprocessor includes instead of modules. So C and C++ have this thing. It's a little bit like modules, gives you most of it. It's just literally dumping stuff in your code with preprocessor includes. There's a bunch of problems. I won't go too much into it. But one is that the includes that you include can themselves include preprocessor directives that can have side effects and other includes, which means that in general, you have to pre-process these for every single translation unit that you're compiling. There are compilers that try to sometimes improve on this, but they only work in special cases, so it's quite normal to have to reevaluate all this stuff every time. And actually, especially with C++, this is kind of fun. You can run, compilers will have a flag that you can use to just run the preprocessor, so you can watch how a few hundred lines of normal idiomatic C++ code turns into thousands of lines of stuff that has to get compiled every time. So yeah, C++, though, doesn't it make some of this stuff better? I think this is probably the most practical pain point with C++, is compilation times is so ridiculously slow. So the preprocessor stuff I just mentioned is part of that, but that's only just making it worse. The real problem is this stuff. So if you get a traditional textbook and compiler design, like the classic Dragon book, it'll give you this really, really nice architecture for building a compiler. So it starts off with, say, Alexa, and that will scan across your code with simple rules finding tokens, such as, hey, that's got digits in it, so it looks like a number, or that's a plus sign, so it's a plus operator. The point is we're using simple rules here to break it up into tokens. And the next stage will be a parser, which would take these tokens and build up a syntax tree out of it. It's all very beautiful and very efficient, but it doesn't work with C++ because of stuff like this. So these are ambiguities in the language. They're two particularly famous examples. The first line is obviously a function declaration. The second one is the instantiation of a class. But you see, there's not really any difference at a high level between the two. You actually have to do a deeper analysis to disambiguate these two. Second one's a bit nastier. So nested templates. So templates in C++ wrap the parameter. Oh, crap. So I lost that. So yeah, templates wrap the parameters with brackets, which right there. Okay, sorry. So templates wrap their parameters with brackets, which looks kind of nice, but gives you this ambiguity when you nest templates because you get, as in that example there, double closing brackets, which needs to be passed as two separate tokens. It's a closing bracket for one template and a closing bracket for the other template, which is ambiguous with a double shift, sorry, a shift operator. So interesting thing about this one is that originally in C++, this ambiguity was removed by making a rule that you've got to put a space in between these brackets. That removes the formal ambiguity, the theoretical ambiguity, but unfortunately people are using this language and they would make this mistake, they would forget to put the space in and then they get weird error messages from the compiler. So the C++ standards folks just gave in and said, look, it makes the language slow, but compilers have just got to deal with this stuff. So now you can write code like that without a space in between the brackets. Oh, come on. And yeah, if you worked with C++, you would have seen this before. Anyone actually want to guess what this C++ error message is for? Yeah, sorry. But even if you could read it, it wouldn't really help that much because it doesn't actually tell you what the problem is. So this one is from accidentally using a set as a map. This is actually quite tame because it does fit on one slide. Even though I have to reduce the font quite a lot, it's quite normal to have several pages. So to be fair, these error messages could be improved as well, but definitely an order of magnitude better than C++. Thanks for listening. Here's another trap. So C++ has a few of these. So we've got a base class that's creating a member function that takes a double. And we derive from that, and we create something that's sort of like an overload using an int. And I say sort of like because if you run stuff at the bottom, what does that do? It actually truncates the 3.141 to an integer and calls the member function from the derived class instead of what you would hope, the one in the base class. So that's actually not C++ to blame there. That's C's quite lax implicit conversion rules happening here. So D has a completely different set of conversion rules. And to be fair, they have a few dark corners as well. But they're generally safe dark corners. They're just annoying things like, for example, if you're working with bytes, if you have arithmetic on multiple bytes, sometimes they'll get converted to ints, and then the compiler will refuse to assign them back to a byte. That's annoying if you're doing a lot of this stuff, but at least it's not unsafe. As for unsafe conversions, I can only think of two myself that are in D. One is between signed and unsigned, and there is work on fixing that one. Another conversion is between ints and characters, which is not totally unsafe, but it's not exactly safe either. Yeah, with C++, the standard library, it really has a batteries not included feel to it. So you have all this cool stuff in the standard library, but as soon as you try to use it, you find you have to write a whole lot of boilerplate code, and this is just normal for the language. So for example, C++ 14 brought out two cool features that we've been waiting for a long time, so tuples and hash maps. Despite the fact that these are both standard library things, you can't actually put a tuple into a hash map without writing your own boilerplate hash function code. And as I said, this is just the way C++ tends to roll. D tends to be much more batteries included. And also, it's not an Apple product. So if you want to replace the battery with something else, you can do that if you want. And yet, ultimately, a lot of this comes down to legacy as well. C++ has a lot of legacy, can't get rid of it. So the problem with the nums I pointed out at the beginning, C++ has a fix for that, but it can't fix the original enum problem. It has to create a new kind of enum called enum class, which means you have to explain to noobs of the language why their code still compiles when they write enum instead of enum class and what the difference is between the two and why we even have these two things in the first place. Which comes back to what I was saying before, that C++ just builds on top of C as opposed to fixing C. So you tend to get this kind of two-layer thing, a high road of nice newer constructs and a low road of C-compatible constructs. So let's look a bit more deeply into one of those and what impact it actually has. So C strings. So try not to go too long with this stuff, but if you imagine in memory is just a big long array of bytes, and we have a string in the middle somewhere. A C string is just pointing to the first character, and then we find the next character, but it's moving along until we hit a null byte, which I've represented with a slash and a 0 there. So a couple of problems we get with this is, one, we have to keep on calculating the length of the string every time we want to do operations with C strings. And another problem is that if we want to take a substring or something like that, we've got to put the null byte in. So we've either got to destroy the original string to put the null byte in, or we copy and create a new string for the null byte in. So either way, we do have performance problems using C strings. C++ strings, you can't actually say too much about them. because the most implementation defined, but they bundle everything together, so memory management, keeping track of the length and all that stuff into one package. These strings are slices, as many of you know, which means that similar to the C version, but instead of using the null byte thing, we actually keep track of the length as well. So what difference does this actually make? So here's a program I wrote once. So it's kind of hard to say what it actually did, but it took a big text file, did some processing of it, and then went into a loop where it answered queries. So if you imagine, say, a word puzzle solver, if you want something a bit less abstract. So you have a dictionary that processes into a data structure, and then you can feed it word puzzles from a newspaper or something. Something like that. So the first time I wrote this, I did it in the classic sort of C++ style, reading in the file in a loop, into a buffer, and then passing the buffer, finding things I'm interested in, and pulling out the strings by copying and constructing new strings. Then I went into the query loop. So this worked okay, but I wanted it to be faster. So I ended up doing a whole lot of optimizations of all different parts of this code. And one part of the code was this part. I replaced it with this. So I did a memory map. So that's another interface to files that you can work with the operating system. Basically uses the virtual memory system. The point was that I could, instead of copying strings, I could slice the strings I was interested in. So slices in D are agnostic about how their memory is made or where it comes from or anything like that. So I can just slice stuff in this memory map and use them as strings, and they're totally fine strings that work with the rest of the D code. Then I went into the loop. So this has taken out a lot of the copying and the allocations from the original code. So the initialization actually worked a lot faster. But that wasn't the really interesting thing about this. The interesting thing that happened was that the main query loop actually got significantly faster as well. So I didn't touch the main query loop in this part. So this is like spooky optimization at a distance. But of course, it wasn't really spooky. It was just because I was packing in the memory in a better way. So in the original code, I was doing an allocation for each string that I was using. So you might allocate a string over there, over there, over there, over there. The point is that they're all over the place, and we don't have control over that. But with this approach, I had all the memory in one place, and computers work much more efficiently with that kind of thing. So this is a cute optimization. Would it work with C? Sort of, you can get part of it. So you can control the memory layout as much as you like. So you can get more efficient memory layouts that way. That's a good thing. But you still need to copy to create the null bytes to make the C strings work. Also, a nice thing about the previous code was that the operating system was managing all the memory for us. So it was able to, for example, share that same memory with other processes. Kind of lose that unless we explicitly use shared memory with C. C++, well, not really so much with C++, because C++, couples everything together into this one package. It means you can't touch it. So there's not actually a lot you can do to optimize this sort of stuff with C++ strings. To be a bit picky, yeah, you can implement a custom allocator to get a little bit of control here, but it's not very practical because you've got to put that into the type. And that means that you created a new type of string that's not compatible with other strings, and that's kind of a pain. And yeah, we still can't effectively reuse the memory mapped data that we have. We can't tell C++, no, please don't create your own copy of this data to make a string. I've already got the data here. So yeah, a lot of people, when they hear about all this nice stuff that D does, they think, surely this has got a lot of overhead, and this D runtime thing I hear about is pretty scary. So I want to make sure that we kind of talk about, what is this D runtime they're talking about. So take a look at this code here, for starters. So as far as I'm concerned right now, there are 4 kinds of code here on the screen. The first one is actually all the code that you actually see on the screen. It's the code that I've written myself. So that's easy. Second one, so at the top I've explicitly imported stuff from the standard library. So I didn't write that standard library code myself, so I'm free to use it. Third one, though. So the compiler will generate some code as well. So for example, we see the new statement, as in the auto greeter equals new greeter. near the bottom there. So that's creating an instance of the class, which, because D is a high-level language, we can do in one line. But of course, it's not a trivial operation. So the D compiler has to generate a bit of code to do that. As a systems programming language, we could write a bit of it ourselves, but we don't have to. And 4. So if the D compiler is writing a whole lot of code for us, in just the same way that when we're writing code, we like to use libraries, the D compiler also uses a library. It's got the D Runtime library. If you check out the code, it is in fact called D Runtime. So this is like a library that gets linked in with your code, which has a whole bunch of routines to help the D compiler implement some of the features of D. Actually, because of templates, it sort of blurs a bit with 3. So some of the code will get injected into your program, and some will get linked in externally, but it's all in the D Runtime library. So this is some of the stuff it does. I won't go into details with it, but see, garbage collection and construction and stuff, it's all there. But we'll emphasize that this isn't something that Walter Bright invented as an idea for D. So C++ has a runtime as well, and so does C. C also has a runtime. And this one, so I think this is a misconception that comes out a bit. This isn't something, it's not like a virtual machine. It's not running in the background. It's really just a library of routines. So to go into that a bit more deeply, take a look at that code on the left. It's C code, but it also happens to be valid D code. So you can take this code and you can compile it with a C compiler, and you can compile it with a D compiler and compare the output. So on the right there is a disassembly of what the D&D compiler gives us. Won't go into full details of it, but it is pretty much what you'd expect from just general purpose computation on x86. The thing to note is that there is no, well, first off, that code isn't big enough to implement a garbage collector, and there's no call instructions there either, so we're not calling into other functions. That is all the code that is running when we're running the code on the left. And in case you're wondering, yes, in a single-threaded program, yes, it really is a single-threaded program. So there really is no way that other code can be running when we're using this code. This is it. And so some people have been this isn't really an official name, I think, but people have been calling this the betterC subset of D. So it's a subset of D that just doesn't need the runtime or anything like that, and it can be used to, as it says on the tin, it can be used as a betterC. So it's all the C-like code, like in the previous slide, but also quite a few nice features of D that happen to not need any of this sort of stuff. And this is an important corollary of what we've been saying before. So the garbage collection isn't something that's running all the time. You can only get a garbage collection happening if you actually explicitly call or do something that calls garbage collection routines. And the main one that does that is a garbage collected allocation. Or you can explicitly call the GC. This is important because it's normal in idiomatic systems programming. If you care about low latency, you're going to remove allocations from your main loop and put them into the beginning. This is an idiomatic thing to do because forget about GC pauses. Dynamic memory allocation has unpredictable pauses as well. So this is normal. And if you do this, you also going to have less worries about GC pauses too. So other things you can do. So I mentioned the GC collect. You can explicitly trigger a collection. There's a bunch of other stuff you can do. If you look in core.memory, you've got a reasonable amount of control over how the GC works. So you can temporarily disable it and enable it. You can even try to improve performance by reserving a bit of memory if you're doing a lot of allocations in some short stretch. So check it out if you're looking at performance. Excuse me. So most D code doesn't need this sort of stuff, but it's nice to know that you got it there when you do need it. Also, D supports a wide range of ways to get memory, so you're not stuck to using the GC. And this is in practice. So you can do all the things you'd hope to be able to do. And yes, it does actually work practically. So there are some languages that give you a garbage collector, and they also give you some value types as well. But they're totally different types, and they live in different worlds, and it's kind of hard to mix and match them. That's not how D works. D works a bit more like C++, in that if you've got an instance of a struct or a class, then it's an instance of a struct of a class. It does not matter how you've allocated it. So this is something you hear about a lot. People say, I like the idea of using D, but this runtime bothers me. I'm doing systems programming. I'm not sure I can use this. I'll emphasize that this isn't just about weirdos trying to rise performance here. We're not talking about those people who, for example, have compiler command lines that long in the hope of getting, say, a 0.1% performance improvement or something like that. This is actually something that kind of matters to some people. So, for example, you might think this way. This is a totally valid way for some people to think. If you've got a server with plenty of grunt behind it, you might not care about any of this stuff. But if you're in this situation, then you might think quite differently. If you, for example, wanting to write decode for a browser. So just remember, different applications have different needs. So some people will want to have a bit more flexibility with how they're using their runtime. So I want to take a look at, this has all been kind of theoretical so far. I want to take a look a bit more about what people have been doing with this sort of stuff. So, you want to do some performance code in D. What can you do? So one approach that works quite well and is used in a lot of code is just stop worrying about the D runtime. So John from eBay wrote a bunch of tools for processing CSV and TSV data. And he gave a talk about it, which is really good. I wanted to link to his talk, but it seems to have been lost. So if anyone's got a copy of it, that would be great, because I think it was a really cool talk. But he explicitly said in his talk that he didn't worry too much about using features of D. Like if he saw a feature and he thought it would be useful for coding, he would just go ahead and use it. And that included the GC. When he wanted good performance, he just made sure he just kept the basics right. So he didn't do redundant copying, extra allocations or anything like that. And he did actually get some pretty good performance. So he got some benchmarks here. At the top, I've got a URL for all the benchmarks. He has done quite a lot of benchmarking. I'm not going to read out all these numbers, but I'll point out the one in the middle there is TSV select. So compare that to GNU cut. So GNU cut is a program that does, it's a C program that does just this. It takes, say, CSV data or delimited data and gives you just, say, one column of it. And that's what the TSV select is doing. So I think this is a good comparison. Apparently, so John stresses that these benchmarks are a bit informal, so I'm a bit hesitant to say this, but apparently he got a 3 times speed up over the C code doing this. And it doesn't look like a fluke, because you see similar sort of speed ups for the other numbers he's got there. He's also compared it to other frameworks like Mork, which is another, Mork and GNU Org, which are also written in C, and a bunch of other toolkits which he left anonymous for the sake of avoiding flame wars, but I think they were written in, say, Rust and Python and Go or something like that. Now there's a popular assumption that a C is like a kind of baseline for high-level language performance. And I think we can challenge that. So it doesn't have to be the case that any higher-level language in C has to be slower than C. I think, especially in the case of text processing, as we see here, sometimes we may be able to get things that are just as fast as C or even faster. And we've actually seen that in other cases as well, so XML parsers and JSON. And that's because there is actually a lot of baggage in C. C is not that perfect a language as we think it is. So another cool project that has been done, the Mir numerical library. So Ilya has been building these. He's been doing it using what's often called the betterC approach. So he's been trying to remove all dependencies on a runtime so that he can create a library that's just like a C library. And I think, I haven't confirmed, but I think he is actually intending, if it gets mature enough, to try and push it into systems like NumPy and R. So even if you're not using decode, you might end up actually be using decode and getting advantages from it sometime in the future, which is pretty neat. So yeah, as I'm saying, he has actually made it so that you can link this with regular C code. It's pretty cool. And of course, yep, he's got the benchmarks. So this is actually a blog post he made, where he's gone into a lot more detail, so I recommend checking that out if you're curious about this. So Mir Glass, you might not be able to read that from the back there, but That's the red circle line at the very top there, which means it's the fastest. Though it's basically on par with Intel MKL, which is Intel's numerical library, which they made made a library that's specially using their Intel platform. And the other things are things like Eigen, OpenBlaz, and Apple Accelerate, which I'm not too familiar with. So we've got some pretty impressive results there. Another cool project, Auburn Sounds. So they've been making some audio plugins, and audio is quite famously very latency sensitive. So they've got a blog, and they've been writing blog posts about how they've been using D for this kind of platform. Spoiler is that it's mostly using the @nogc attribute, which causes the compiler to verify that you're not actually doing any sort of GC allocations, and therefore have no opportunities for GC pauses. Another alternative, I couldn't find an original project to the site for this, but it's a popular approach for games. So if you're doing a game, chances are you already got your audio in a separate thread, and you can actually detach a thread from the GC and runtime. So that means that if you get GC pauses in your main code, you're not going to interrupt your audio. PowerNext, another project. So this one is a kernel, getting a bit lower level here. So a kernel for an operating system that's still in development, but it's intended to be just basically a D operating system for 64-bit x86. So this one works using the minimal runtime approach. So we've got a stub minimal runtime that can be ported to bare metal, so it's not dependent on anything higher level like operating system or C. Yeah. As I said, it's still in progress, but it's actually looking pretty cool. By the way, you can actually get this package yourself. This is a package that's available on GitHub. Should have put the link there. Finally, this is actually a project I worked on. So the previous one was what in embedded systems terms is called a hosted embedded system. It means it has a runtime. I had to go just experimentally try and get a freestanding version. So that means you take out all the runtime, that's the D runtime, C runtime, and the operating system. So this was just me hacking around trying to see, what if we could use D as a betterC right on bare metal. So it's a pretty short game, but it was just playing around trying that out. And I wrote a bit of a write-up talking about pros and cons of using D in this sort of way. And if you still want more stuff to read up on, a couple of things I recommend. So Weka.io last year gave a really good talk about using D for their distributed data storage system. And so it's a good talk because they talked a lot about both the pros and the cons of using D for this kind of thing. So it's good if you're interested in that sort of question. And there's also VibeD. It's an event loop-based web and network application framework. It's a blog post about that. And that's what I got to talk about. So that's my blog where I'll keep on talking about this stuff because the reason why I wrote the same thing was that I thought maybe if I do this stuff and I document it, maybe other people will try it. And if other people try it, maybe we will one day have this as an officially supported D as a betterC sort of thing. So I'm going to keep on writing about this, and I encourage people if they're interested to talk to me about this. So I think this is useful. So you can check out my blog. Also, I do consulting in Sydney. So if you're interested, you can contact me on that there. But any questions? How much time have we got? Yeah.
An objection that's raised frequently in discussions on how can use Reddit and so on is, well, it's completely impossible because libraries use QC, Phobos uses UC. Could you sort of clarify a bit in practice how you see that?
So can you just repeat that? I got most of it, but can you repeat that?
A frequently raised objection is that it's all very well to be able to write no GC code.
Yeah.
And we've done that ourselves with an Excel wrapper that allows you to. So it's fine, but for others it might be helpful to explore a bit in practice, whether you're working with Phobos or other libraries, how much of a problem is is libraries using GC versus.
Yeah, I think I understand the question there. So yeah, so you can use Arneaud GC, and that will make the compiler verify that, yep, you're not using any garbage collections, but of course that prevents you from using third-party code that does do garbage collections. Yeah. So that's, I think it's a work in progress. So honestly, I'm not totally up to date to it. When I was writing Xenthi, I found, actually with Xenthi I didn't use Phobos at all in the end. So in practice, you can use a lot of stuff in Phobos and Xenthi, but the biggest blocker definitely is exceptions, which means that a lot of stuff, at least now, you can't use. So an example of that is the date handling stuff. So date handling itself doesn't seem to explicitly use GC, but actually because the date handling will throw exceptions, you'll have GC for that. So Walter mentioned in his previous talk that he's looking to push a fix for that, so that we'll be able to have exception handling without GC, and that's going to open up a lot of stuff if that goes through. So yeah, at the moment there's a bit of a limitation there, but hopefully things are going to look better in practice pretty soon. Next question.
Okay, so one of the reasons why C stays super popular as the low-level systems language of choice is because no matter what crazy architecture you're trying to target, you can pretty much guarantee there's a C compiler for it. And you might love to use a better language, but if you can't actually build code for that target architecture, it's no good. So what are the particular challenges here for D? What are the things that can be done to resolve that issue?
So for starters, both GDC and LDCs do support quite a few CPU architectures. I think the biggest one probably is the runtime. Unless you're doing the freestanding stuff like I did, you got to port the runtime. So the stub runtime that I mentioned before, I haven't actually done D on ARM, but I think there is a port so you can do that on ARM. But yeah, definitely the runtime is going to be the biggest blocker. Especially, so if I can do a bit of preaching myself, I would like if we can keep the runtime fairly portable as well. So try not to have too many system dependencies in the runtime so that we can do practical programming on different platforms. And this isn't just weirdo embedded stuff. It's also stuff like mobile platforms and stuff like that. If we have an assumption baked into our runtime that it's running on a server or a desktop, then we won't be able to use D so flexibly. So it's a call from me as well. So yeah, I think I would say it's basically the runtime. Because so LLVM supports a ridiculous number of architectures. So yeah, I think the runtime is the biggest blocker. And by the way, so D did used to support 16-bit Windows once upon a time. It doesn't now. I don't think it supports any 16-bit platforms officially now. But maybe one day we'll be able to again because it was at least originally supporting that. So see how that goes.
Simon, we have a question from the chat.
Yep.
From Mio Iwakura. Is it possible to alloca with no runtime?
To allocate with no runtime?
There's not a T and an E at the end of that word, but yes, I guess so.
Okay. So, well, it depends what you mean. If the D runtime, yeah, you can use malloc and stuff like that, but of course, you can say that's using the C runtime. So yeah, you can totally use the C allocations, but I guess is what the person's actually asking. Yes, you can use malloc and free.
There's a continuation to the question.
Yep.
I tried copying rt.alloca into my runtime free project, and it segfaults.
So I can't debug that right now, live on stage, but yeah.
And
recommend posting that on the D-Lang forums to learn. There will probably be someone who can help you with that.
I think Mio has misunderstood me. I did not say malloc. Alloca is the stack allocator.
Oh, hey, right. Yeah, I think I saw that thread. Yes. Sorry, I misheard that. Yeah. Yeah, so I saw someone posted that on the forums lately, and I've been traveling, so I haven't looked into it. So yeah, I don't know the answer to that straight away. It should be possible, but obviously there's some bugs there that needs to be ironed out. So see how that goes.
Cool, thanks, Simon. I think we got time for 2 more questions at the most.
Go.
Hello.
Hi.
As you know, the D runtime is not just as a repository or a library. It's not just a library of runtime code, but
Yeah.
it contains a bunch of bindings for the different like C bindings.
That's right, yeah.
Do you have any opinion on that? Is that the place to keep all these, or should it be moved somewhere or forward or whatever?
So stuff like bindings to the C standard library is not too scary, but stuff like curl and I think there's zlib and SQLite in there as well. Yeah, it would be nice. I mean, I'm not going to say just get rid of that, but it would be nice if we didn't have stuff like that, or we sort of kept that under control, or at least had a way to get rid of it when we point to other platforms. So yeah, that is actually the kind of thing I was talking about when I said please keep dependencies out of the runtime. That is actually a good example of what it is. Yeah, if you put C libraries in there that only, for example, work on a particular platform, then you are effectively saying the runtime can only work on this platform. So it's better to have stuff like that in Phobos. And I think actually a lot of that stuff originally came from when D was very, very new, and we didn't have libraries for stuff. Nowadays, D is a bit more mature, so I think there's less motivation to put stuff like, deadlib and curl in there, because people say, why don't we have a D alternative? Why are we putting bindings to stuff in there? So I think even if it's without people like me whinging, we are probably going to see less of that in the future. So, yeah. Anyone else?
Thank you, Simon. Right, so we'll take another quick break, and then we'll come back to have our third speaker before lunch.